The second section today, section 5.3, is learning the last way to solve systems of equations, which is solving these systems by elimination. Just like substitution, if we look at the beginning of the word elimination, it has the word eliminate in it, which means cancel out. So we will be canceling out terms to solve these equations. We have one more flow chart to help us work our way through these situations. So let's say perhaps we have the system x plus 3y equals 17. This is written in standard form. And negative x plus 2y equal to 8. This is also written in standard form. When both equations are written in standard form, you're going to want to use elimination. It's generally faster. What you are looking for once they are in standard form is to look at the equation and decide if any of the variables are equal and opposite. Underline those right here, equal and opposite. Do you notice that the x and the negative x are equal and opposite? Meaning they're the same coefficient, an invisible 1, but I have one of them being positive and one of them being negative. If that's the case, then we answer yes. Since we found those equal and opposite variables, what we will do is we will add the equations together. It feels so wrong, but is absolutely allowed in math. So here are the two equations, and I'm going to add them like good old-fashioned elementary school math. I'm going to add them together. X minus x eliminates, hence the word elimination. 3y plus 2y is 5y, and 17 plus 8 is 25. I have one equation with one variable left. I can continue to solve. Okay, we're solving this short, tiny equation from step 3. To solve this tiny equation, we would divide by 5. Therefore, I have y equal to 5. That is half of the answer. To find the other half of the answer, I will take this value 5 and I will substitute it back into the original equation, much like the last step of substitution. Here is the original equation, and I'm going to substitute instead of y, I'm going to put a 5, since that's what y is equal to. This would become x plus 15 equals 17, and then x equal to 2. That is the second part of my solution. If I was worried that I didn't get it right, I would check my work to make sure that this solution 2, 5 is the right thing by plugging them in. Here's the first equation I had. I think that the x variable is 2 and that the y variable is 5, so I plug those in. And I'm trying to decide if 2 plus 3 times 5 is equal to 17. But by doing this math, I can see that this ends up with a mathematical sentence, 17 equals 17, which is absolutely true. I'll plug them into the second equation. Negative x plus 2y equal 8. This would be negative 2 plus 2 times 5 equal to 8. We're trying to decide if negative 2 plus 2 times 5 equal to 8 is a true mathematical statement. Because if it is, like 8 equals 8, we have proven that this point makes both equations true and that this is the point of intersection between these two standard form equations. Take a second and glue this into your spiral, and we will meet on the next page. Our first example today to work on elimination using the steps from that flow chart is to look at the equation 2x plus 3y equal to 10 and 2x minus y equal to negative 2. These are both written in standard form, alphabetical order. Number x, number y equal number, both of them. Do you notice, just like in step 1, that these x terms are equal and opposite? They are the same coefficient of 2, but one of them is positive and one of them is negative. That's good. That's what we want. So we will come over here and we will take 2x plus 3y equal to 10 and negative 2x minus y equal to negative 2 and add them together. When I do this, the 2x's will cancel. They will eliminate. I continue going. 3y plus a negative y is 2y, and 10 plus negative 2 is 8. Very quickly, I'm down to a small equation that I can solve easily for y. Divide by 2 on both sides, and you get y equal to 4. Is that the whole answer? No, a solution is a coordinate, so I should have both a y value and an x value. And I get that x value by plugging in my answer. You can choose to plug this into either of the first two equations. I always choose the first one out of habit. That choice is up to you. But you must make sure that you plug it in for the correct variable. Once I've plugged it in for that correct variable, I'm only left with one unknown, which means I can solve. This would be 2x plus 12 equal to 10. And then by subtracting 12 from each side, I'd have 2x equal to negative 2. And dividing by 2 on each side, I'd have x equal to negative 1. Which means that my final answer and my solution to this system is what? Negative 1, 4. Making sure I write them in x, y, like a coordinate should be. That is the point of intersection between these two standard form equations. Here's one to try on your own. Go ahead and give it a shot. Identify if you have them in standard form, if there is a variable that is equal and opposite, and begin solving. Right away you can notice that the 3y and negative 3y are equal and opposite. That means that is the variable we're going to cancel out. So we would write the two equations on top of each other like a good old-fashioned addition problem and add all of the like terms together. 5x plus x is 6x. 3y minus 3y eliminates, and 9 plus 9 is 18. So simple to solve. We would divide by 6 on both sides, which would give me x is equal to 3. There's the x term of my solution. I still need the y term, and I would solve that by plugging this in for one of the original equations. Again, you can pick either of the two equations. I just like picking the first one out of habit. Do I plug this in for the x or for the y? Since I found an x term first, I don't know what y is still, but I can plug it in for x. This would be 15 plus 3y equal to 9. Subtract 15 from both sides would be 3y equal to negative 6. Divide by 3, y equal to negative 2. So you should have gotten that the point of intersection, the solution to this system, is 3, negative 2. You can always check your work by plugging in this x and y value to both equations and making sure they make sense, or solving for y and graphing. Two more examples, some special case scenarios. Let's say you have 2x plus 3y equal to 8 and negative 2x minus 3y equal to 20. And it says to solve the system. You would notice that these are in standard form, alphabetical order, and you'd say to yourself, I'm going to solve this by elimination since I notice that I have an equal and opposite variable. So I'll take the two equations, 2x plus 3y equal to 8 and negative 2x minus 3y equal to 20, and I'll add them together. That equal and opposite variable cancels out. But check what happens again. Those are also equal and opposite. I have 0 plus 0, which gives me 0, equal to 8 plus 20, which is 28. Is that a true mathematical statement? No, 0 does not equal 28. And since that is a not true, you would say that this system has no solution. If a system has no solution and I graph them, what would you see on your graph? Whatever these lines are, somehow they're parallel to each other, which means they will never touch. If we were to graph it and see it like this, we would also notice that it has no solution. The last example today in the final special case scenarios, let's say we have 5x minus 3y equal to 5 and negative 5x plus 3y equal to negative 5. We say to ourselves, this is in standard form, both of them, and I notice that I have an equal and opposite variable. Since I have an equal and opposite variable, I can add these together to start solving by elimination. I add the two equations together like a good old-fashioned addition problem, and I eliminate my equal and opposite variables. Uh-oh. Guess what's happened every single time? They all canceled out. If they all canceled out, you're left with 0 on the left-hand side and 0 on the right-hand side, and the equation now reads 0 equals 0. Is that a true mathematical statement? Well, yes, 0 equals 0. And if you're left with a true mathematical statement at the end, you would not say it has no solution. You'd say it has infinitely many solutions.